About questions about your homework. I'm assuming there are a few. What did y'all have? You had 1, 2, and 19 through 24. What you got? (20C). I got a particle that moves along a line so this position at any time is S of t equals negative t cubed plus 7t squared minus 14t plus 8. Everybody's okay with the instantaneous velocity, which is just the first derivative? That's part A. Part B is the acceleration, which would be the derivative of the... Sure. So part A asked me for the instantaneous velocity, which is just the first derivative of position, which would be negative 3t squared plus 14t minus 14. And part B asked me for the acceleration, which is the derivative of velocity, which is the second derivative of position, which will be the derivative of the part A, right? So negative 6t plus 14. Then part C says, when is the particle at rest? So when does, and I feel like this is on your blue sheet, I'm not sure. Yeah. When is the particle at rest? And if you have to use this to reference right now, it's A-okay, because you'll do it so many times you'll get used to it. When is the particle at rest? When what happens? When velocity equals 0, v of t equals 0. So I want to take the velocity equation, which is a quadratic, which we should be very comfortable with. When does this equal 0? So I probably want to try and factor if I can. I don't know if this factors. It looks like it does not. Is this a calculator problem? This is a calculator problem, so maybe I graph it and find the zeros. Or I can do the very favorite option, which is the nasty quadratic formula, right? Either way, I think I will graph it and find the zeros because I prefer. All right, so graph, find the zeros. You will find this is should be an upside down parabola. When you graph it, you get t is approximately, and I'm going to cheat and use what they were giving me, 1.451. Of course, that is in seconds, right? Yep. And then the other solution is 3.215 seconds. What could have happened at those 2 points? He could have changed directions, or I always say he, because remember, that's my bug I keep thinking about. Or he could have just stopped to rest. Okay, it could have been one of those bounced off the x-axis type max or mins instead of going straight through when we talk about the position. Okay, describe the motion of the particle. At what values of t does the particle change direction? So we're going to need to do a little sign analysis here to see exactly what's going on. So this is my velocity, which is the derivative of position, and up top I'm going to do my position so I can tell what exactly is going on. And I'm going to put the zeros of velocity, or the zeros of the derivative, which there are two, 1.451, 3.215. Now remember, if the derivative is positive, that means I'm increasing on my function. The derivative is negative, I'm decreasing, and if it's 0, then it's constant, right? So we're going to use that kind of reasoning and see if we can figure out what's going on here. So and if you already have it graphed, this is pretty easy, okay? Because if you've got the derivative graph, let me just graph it now and I'll show you. Negative 3x squared plus 14x minus 14. This is what I like about a calculator problem with one like this, because it's a little easier. You don't have to do a lot of calculating yourself. So I've already gone in, I calculated my zeros, right? It happens here and here, there's my 2 zeros. So to the left side of the 1.4 or whatever, is the function positive or negative? It's below the x-axis, so what is it? Negative. So it's negative here, which means all of this is negative. Remember, this is the graph of the derivative that I'm looking at, not the position function, but the graph of the derivative. So that tells me agree or disagree? Y'all okay there? Now, between 1.4 and 3.2, what exactly is my graph doing? Is it positive or negative? It's positive, right? It's above the x-axis. So that means here, oops. And then same thought. Now, if you didn't have your calculator, let me go ahead and finish this. This would be negative on this side. I'm not looking at the slope now, remember. I'm looking at, is the function itself positive or negative? Because this is the derivative. So this is negative and negative forever. And if I graph my position function, it should show that. It should show that I'm decreasing, increasing, and decreasing again. And just to show you that I'm not telling a story, negative 3x doing the same one again. Negative x to the third plus 7x squared minus 14x plus 8. I'm decreasing until I get to this 1.4. Then my function is increasing, right? And then it's decreasing again. So do you understand how to look at the difference between the function and the derivative? Does that make sense? Are y'all okay? I feel like no. I feel like y'all are like whatever. I'm not. Am I speaking Greek? Does this seem sure? Y'all are okay? Okay, so that's not all you have to do, but that's the work behind finding those intervals is what I'm saying. So it says describe the motion of the particle at what values, and this is kind of what we're going to work on today, writing this and telling what happened. So remember I start at t equals what? 0. I don't go beyond 0 because time doesn't go backwards, right? So from time t equals 0 to t equals 1.451 seconds, the particle, if the function's increasing, which way is my particle moving? I think this is on there. Look at your sheet. If velocity is positive, the particle's moving right. If velocity is negative, the particle's moving left. So from 0 to 1.451, and I should probably, this might help you if I put a 0 here, the particle is moving, you said backwards, moving to the left. Then it stops, right? So at time t equals 1.451, the particle, and I should really say here, this is a big thing on FRQs. From time t equals seconds, the particle is moving to the left. You have to say why. Because velocity is negative on this interval. I told you you're guaranteed an FRQ with particle motion, and this is what they're looking for whenever you, it might say, on what intervals is the particle moving right, on what intervals is the particle moving left, why? And so you'd have to say, because velocity is da-da-da, or because the function is increasing, or any of those would work. Then at time t equals 1.451, 451 seconds, the particle stops because velocity is 0. The particle changes direction. You won't have one that you have to write this much, but this gets you used to whatever they might ask you. Changes direction at this time. Why does it, how do I know it changes direction? There's a sign change. A sign change in what? Velocity. Because velocity changes signs. This is a big one. That one comes up a lot. At what point does the particle change direction? Well, every time it's 0. I'm still not done. This only describes up through here, right? Then I would say from (1.451 seconds), 3.215 seconds, what's the particle doing? Right or left? Right. Why? Because velocity, and I'm actually going to shorthand this a little bit, is greater than 0 for positive. At 3.215 seconds, the particle changes direction. Why? Because velocity changes signs, and you could actually, if you wanted to come up here and say that it changes signs at this time and this time, that's fine too. And then what happens? Then the function decreases forever or until it stops, right? So then from, because it doesn't tell me how long it moves, or it just says t is greater than 0. From t equals 3.215 seconds until, I'm just going to say the end, the particle moves which way? Left, because velocity is negative. It's a lot of writing, right? Just because we're already here. Where did my little bug start? Where was he at the very beginning? 8. How do you know he was at 8? That's exactly right. If you plug in 0 for t for the position function, you'll find 8. So that's where he started. So he started at 8. He moved to the left for 1.451 seconds. Then he stopped. He changed. He turned around and went the other direction. Then he stopped at 3.215 seconds, and he changed directions, and he went back left again. Does that make sense to everybody? What we're doing? I know that's a lot. So, like, I'm not asking any more questions because that was ridiculous. While we're here, I can't really do that yet. Okay. What else from your homework? It's more of this. The problems will just get a little bit more involved. But same kind of thing. There'll be more, instead of just straight up a particle moves, it'll be more application type stuff. A rocket is launched into the air. This is the position. But it's still particle, it's all particle motion. Anything else? So 20, 21, and 22 were almost exactly the same thing. 23 just asked you to find the acceleration when velocity was 0. So after you found these points, you plug them into the acceleration equation. Same thing with 24, but you just did the absolute value of velocity. So any other questions there? Y'all okay? How you feel about particle motion so far? Bad? Do you feel bad? Bad as in making the connection between position, acceleration, velocity, or bad as in it's just a lot of work, or bad as in okay, I get it. It is confusing. It will, but it is it does get very confusing because there's so much to remember with particle motion. All right, y'all want to take a break before we do the yeah. Number 2. Oh, gross! I forgot about these. Write the area of a circle as a function of the circumference. So first off, how do you find the area of a circle? Pi r squared. But what they want me to do is area as a function of the circumference. Well, how do you find circumference? 2 pi r, right? Or pi times diameter. So what I can do is I can solve this, and this is getting us ready for related rates. It's just doing it early. I can solve this for r, right? And then I can take that and plug it in this equation. So this would be c divided by 2 pi. And now I'm just going to replace this r with c over 2 pi. So I get pi times c over 2 pi squared, which would be pi c squared over 4 pi squared. I can take out one of those pi's and get c squared over 4. So area as a function of circumference would be circumference squared divided by 4 pi. This, because this whole thing is squared, c over 2 pi, so the top and the bottom is squared. Find the instantaneous rate of change of the area with respect to the circumference. So derivative of the area with respect to the circumference. Remember, this is just a constant here on the bottom, right? In fact, I could write this as 1 over 4 pi times c squared. And for me, that's a little bit easier to find the derivative of than what we have. So if I do that power rule and I multiply by 2, I have 2 times 1 over 4 pi times c. That would be to the first power. 2 over 4 is a half, so I get 1 over 2 pi c, or c over 2 pi, either one of those will work. I do need to make sure, nope. It makes sense or no? Confusing. So I did the power rule, so I took this and I multiplied around. So 2 times 1 over 4 pi times c, and then I subtracted 1 from the exponent. So then here, this would be 2 over 4 pi times c. 2 divided by 4. That's the derivative, yeah. It's more of doing that same product rule. That's the thing with these problems, is they give you this easy little rule, and then you have to do it for these really complicated functions. This is the derivative of a with respect to c. Yes. Part C said said evaluate the rate of change of A at C equals pi and C equals 6 pi. So I'm assuming I'm still doing instantaneous rate of change here, since we calculated that before. They should probably definitely put that in there. But at c equals pi, all I'm doing is plugging into this dAdc I already found. So I get, so dAdc when c equals pi would be pi over 2 pi, which is, of course, just 1/2. And then derivative of a with respect to c when c equals, what was the other one? 6 pi, 6 pi over 2 pi, which is, and D was just a units question. It said, if C is measured in inches and A is measured in square inches, what units would be appropriate for the derivative of A with respect to C? So it said area is in inches squared, circumference is in inches. So what would my units for both of these be? Inches squared per inch. Derivative of A divided by, or derivative of A with respect to C. So you essentially just divide the units there. Same thing, inches squared per inch. Which it seems like that would be inches, but it's not, because that's how the area is increasing or decreasing in relation to the circumference. Y'all look like you are just, it's just going, yay or nay, what you think? Y'all got to get a little peppy. Yes. Anything else? In the 20s, the 20 through 24 or whatever? Yes. But they'll be in the form of word problems, like just a little bit different. We're gonna work through some together. Yes, yes, yeah. We're gonna add a little bit of stuff to it, speeding up, slowing down, that kind of stuff. But other than that, I know, I'm sorry. But I told you we're gonna park here for a few days, and we will. We'll stay on particle motion for at least through tomorrow, maybe even through Wednesday. We'll see how y'all are getting it. All right, Khalil, you need a break? Yes. Okay. Before we add anything to this or make it any harder, let me ask you a few questions. When you're talking about particle motion, you start with a position equation. LT, that's my position. How do you find, and we already answered this a little bit ago, where you started? 0 for what? T. Because that means that's time 0, right? How do you know which way you're moving? Signs of what? Velocity. That's exactly right. Signs of velocity. So when velocity is positive, that means I'm moving which way? To the right. And when velocity is negative, I'm moving to the left. When do you stop? When what equals 0? Velocity. Everything's coming back except velocity, right? Velocity. When do you change directions of velocity? What happens if velocity is 0, but from the left and right of that 0, it never changes signs? It just stopped. It just stopped and rested, but then it kept going in the same direction. How do you find the speed at a point? Let's say the speed at time t, just any particular value. Acceleration's close, but acceleration tells you how much you're increasing or decreasing on your velocity. Anybody else know? Absolute value of velocity. And if you think about it, can velocity be negative? Sure, but speed can never be negative. You can't go negative 45 miles an hour down the road, right? But you could have a negative 45 mile per hour velocity, because if I'm going backwards instead of forwards, right? Because that sign of velocity tells me which direction I'm moving. Does that make sense? How do you know, we haven't talked about this, how do you know if you're speeding up or slowing down? Okay, so you're really close. It does have to do with acceleration. I'm kind of setting y'all up on this one because we haven't talked about it. Speeding up happens when acceleration and velocity have the same sign. It doesn't matter if they're both negative or both positive. As long as they have the same sign, then you're speeding up. If acceleration and velocity have opposite signs, that's when I'm slowing down. I think this is on your sheet, but I'm not completely sure. It's not. You might want to write that on there because that's almost always asked. When are you speeding up? When are you slowing down? So I have to compare velocity and acceleration to position, or not to position, but to each other, and find out, and then I may have to find out when that happens or where that happens. So when is time? Where is position? Trying to think of anything that might come up. Where? Okay. Let's look. I hope this will help you just a little bit. Look at the worksheet that I just gave you. That first graph looks something like 2, -4. This goes to 1. It goes up to 1. Most of the time on an FRQ, you're going to be given the graph of the derivative and asked to do stuff with it. This is the graph. This is the graph of position, which is a little bit easier to work with. 4, 2, and then over to 5, right on 2, 7, -2. So I've got this graph, right, in this very first one, and it says, when is the particle moving to the left? So this is the graph of position. When is the particle moving to the left? What tells me left or right? Left is when what happens? What do we say over here? Velocity is negative. Velocity, this is not the graph of velocity, so I can't just look at when this is negative. So what am I looking for when what happens? Negative slope. So looking at this graph, where is my velocity negative? Is that number wrong? I'll just have to put this paper up here. So hold on a second. Sorry, y'all. Clearly, I can't even draw a graph. Find it. All right. So we said when velocity is negative, it's moving to the left. So for this one, I'm looking for a negative slope, which is going to happen here, right? This is when my slope is negative, which means my velocity is negative. So when is it moving to the left? It's moving to the left from t equals 5 to 7, right? So I'm just going to say 5 to 7. How about when it's moving to the right? What am I looking for? Positive slope. So where is that happening? 0 to 1, and then 3 to 4. Does that make sense? When is my particle standing still? Where? 1 to 3. Is that it? 4 to 5. Yeah, because this is the graph of position, right? And so the derivative of position is velocity. So if the slope of this one is negative, that means velocity is negative. Does that make sense? Because my relation is position, velocity, and acceleration, each one taking a derivative of the prior. All right, now we get to the good stuff. Graphs of particles' velocity and speed were defined. So let's look at velocity first, because velocity is kind of a little bit easier for us to get here first. All right, as I look at this, remember velocity is simply the what? Derivative of position. And derivative is nothing more than what? Slope. So if I have position here, so look what I have. These slopes are easy, right? Because that slope is 0, that slope is 0. What is the slope of the first line, though? That first little line segment where I'm moving to the right with this positive slope, what would that slope be? 2. Agree or disagree? Okay, how about the next little segment? What's the slope there? I'm going up 1, 2, and over how many? 1. So what's the slope? 2. Oh, I wrote, sorry. What? This slope is 1, this slope is 2. No, no. This is 2, this is 4. right? Because I'm going up. Yeah, because I'm going by 2's instead of 1. I'm losing my mind. 2, 4, and over 1. Sorry, Hope. You're right. And I'm sitting here going, nope, nope, nope. How about this last one, this negative? Negative 2. So now all I have to do is graph those. So from 0 to 2, or 0 to 1, excuse me. From 0 to 1, what's my velocity? 2. So from 0 to 1, my velocity is 2. That should be a straight line. And then from 1 to 3, my velocity is 0. And then from 3 to 4, what's my velocity? 4. And then from 4 to 5, I'm back at 0. And then from 5 to 7, negative 2. 5 to 7 is negative 2. Does that make sense? Yes. All right, how about the last part? How about speed? Just absolute values. So it's the exact same graph, but any part that's negative, I'm just going to reflect it up. So this is going to be, it's going to look exactly the same. Here, here. What is that at 4? Here. The only difference is this one, instead of being at negative 2, it's going to flip it up to positive 2. We'll come back to moving the fastest shortly. What do you think it is? When do you think you're moving the fastest? Why? Speed's the greatest there. Are y'all okay? Let's apply it. Now it gets fun. Hang yourselves now. I'm getting way too excited. This is the only class I get to teach in today, so I gotta make it. They're testing and they talked me into pushing it back. I'm a softie now, apparently. I was supposed to say, no, you're not. Thank you. Before we do an application type problem, let me show you this. I have this in here now to show you too. No. 1, 2, and then 3, 4. This is a graph of velocity. Tell me, you're going to have to really think about this. Tell me where you think my object is speeding up. Let's do this first. Where does velocity change signs? 2, right? So from here to here, velocity is positive. Agree or disagree? And then from here to here, velocity is negative. Agree or disagree? How about here? It's still negative, right? This is the graph of velocity. This time I'm not giving you the position graph. I'm giving you the velocity graph. So I'm just looking above or below the x-axis, positive or negative. How about from here to the end? Positive. Now, how do I tell if something is speeding up or slowing down? Yes, have the same sign. Velocity and acceleration have to have the same sign in order to be speeding up. I don't have the graph of acceleration, so what am I going to do? It's just slope, right? It's the slope of velocity. So here, this is a constant slope, agreed? Positive or negative? So this whole sign, acceleration, is negative. How about the other side? It's positive. So where on this whole interval, and I'm just looking from, we'll call that 8. So from the interval or on the interval from 0 to 8, where am I speeding up? 6. Why? Velocity and acceleration have the same sign right here. They're both positive. You see that? Is that the only place I'm speeding up? Even though they're both negative, I'm still speeding up because they're the same. Does that make sense? So I move, the velocity is positive. From 0 to 2 seconds, I move to the right. Right? I stop, but I don't change direction. That's where velocity is 0, but velocity is not changing signs. They are going straight through, right? Velocity, I'm sorry, I do change direction. Oh, wait. Burn. So I do change direction at 2. But acceleration is constantly negative there. So then I speed up at 2 seconds. I speed up, but I'm still going in the same direction. I'm still moving left. Does that make sense? Okay, let's do a word problem. This is number 18 from your homework. Launching a rocket. And I'll do this one and I'll stop. Let y'all work. Oh, I probably need to just show you this graph. Draw it. Yo, this thing's fixing to give me like 3rd-degree burns up here. What's that? Avery and Alex are missing so much fun. Don't we miss them? All right, launching a rocket. When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upward for a while and then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket to keep it from breaking when it lands. The graph below shows velocity data from the flight. So let's see if we can velocity, right? All right, so it looks like my velocity is positive here, yes? It doesn't change signs until I hit about 8 seconds. What could cause, if you think about what this is, so a model rocket's launched, propellant burns for a few seconds, accelerating the rocket. So acceleration is positive because slope is positive, right? Then acceleration starts turning negative after that accelerant burns out. And then at the very end, an explosive pops, which causes more acceleration, so the acceleration is positive. Does that make sense to you? Do you see what's happening here? So the first question is, how fast was the rocket climbing when the engine stopped? Well, where did the engine stop? So you can see the word problem. Burns for a few seconds, accelerating the rocket upward. After burnout, it coasts upwards for a while, then begins to fall. So it's up, it's still going up, and then it starts to fall. Where does the engine stop? About 2 seconds. Does everybody see that? How fast was the rocket climbing when the engine stopped? Remember, this is velocity, this is not position. So how fast do you think it was climbing when the engine stopped? About 190. Then the engine cuts off. How many seconds did the engine burn? 2, about 2 seconds, right? So at about 2 seconds, the engine cuts off. When did the rocket hit its highest point, and what was its velocity then? What happened at 8 seconds? It stopped accelerating, right? So when did it reach its highest point? At 8 seconds. Does everybody see that? That's when velocity is 0. So that's whenever it changes. Remember, when velocity changes signs, position changes direction. It stopped going up and started going down. Or it stopped moving right and started moving left, right? Same thing, I'm just up and down now instead of left and right. Are y'all okay there? So at 8 seconds, that's when, so I'm still going up here, right? I'm still moving up, just maybe not in the same speed I was before, or the same velocity I was before. All right, so 8 seconds is when I stop. What was the velocity then? Well, what's the velocity anytime you stop? 0, and that makes sense. Are y'all tracking with me? When did the parachute pop out? Because remember, it goes up in the air and then the engine stops, but it's still going up even after the engine stops because it has so much built up force going up. Then it stops and then it starts coming down, but then a parachute pops out after it's coming down. Well, we know this is when it changes direction and starts coming down, right? So it's falling, falling, falling. When does the parachute pop out? 11 seconds. It looks like this is about where it happens. You see the change in velocity then? It's not a constant velocity anymore. The parachute pops out and kind of stops it from such a constant velocity. How fast was the rocket falling when the parachute popped out? But because I said how fast, I'm talking about speed, so it'd be 90 feet per second. That's exactly right. The velocity was about negative 90 feet per second, but the speed would be 90 feet per second, right? How about, how long did the rocket fall before the parachute opened? About 3 seconds. That's exactly right. Remember, this is where I start falling. Up, 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 up until I get here because velocity is positive. I know that this is confusing because I'm up and down, but you have to remember this is not position, this is velocity. This is a good question. This is the last one of this one. When was the rocket's acceleration the greatest? What are you looking for? The slope, right? I'm looking for the biggest positive slope on this graph. Where does it look like that happened? About 2 seconds, right? I almost have a vertical tangent there. It's really, 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 really steep. So I would say about 2 seconds. So right before that engine cut off, right? That's whenever I had the greatest acceleration. When was the acceleration constant, or was it ever constant? After the engine cut off, but before the parachute came out, right? Because the slope here from 2 seconds until 11 seconds, the slope is constant. And that's really what I'm asking. When I say when is acceleration constant, then I'm really asking you, when is the slope constant on velocity? Does that make sense? Are y'all sure? I didn't really write a lot for that. I just want to talk you through it and make sure you understood what that was asking. Okay, I'm going to stop there and give you some practice.